Okay, in this video, I want to talk through and refresh your memory on what is called inertia balance. So we did this lab in class, and we've actually done this AP free response problem also, but I think it's worth a refresher here right before our AP exam. So the main concept that you're being tested on in this situation is, do you know the difference between gravitational mass and inertial mass? So when we measure the mass of something in our everyday life, we have tools that depend on gravity. Like I set the mass on an electronic balance, or I set the mass on a triple beam balance, and I'm expecting that mass to create a downward force and create some weight so that the balance can measure that mass. But if I was out in space where I don't have any gravity, I have to measure mass a different way. So I'm going to be measuring mass based on its inertial property, meaning that inertia is resistance to change motion. So I'm going to take that mass and I'm going to set it on something that boings. So in class, we did something that boinged back and forth. In this particular example, we're actually boinging something up and down. But if the mass was heavy, it's going to end up boinging slow, like boing, 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 or boing, boing, boing. But if the mass is light, it's going to go boing, 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 boing. And so the period can tell me about the mass. So the equation that's got to pop in my head when I'm talking about inertial mass is T equals 2 pi m over k, square root of m over k. So I'll put that down there. All right, so I gotta have quickly read to get us back all caught up. A thin flexible metal plate attached at one end to a platform can be used to measure mass. When the free end of the plate is pulled down and released, it vibrates in simple harmonic motion with a period that depends on the mass attached to the plate. So that's where they're giving me a hint that this is the equation. To calibrate the force constant, that means to determine the force constant, and the force constant is another name for K, the spring constant. This one's really not called a spring constant because it's on a boingy piece of metal instead of a spring. So they're using force constant. But so in order to determine K, objects of known mass are attached to the plate and the plate is vibrated, obtaining the following data. So when I put a 0.1 kilogram mass on it, it took 8.86 seconds to make 10 complete boings or vibrations. And so it's too hard to measure the time for one vibration, one complete boing. So we usually do it by 10, and then to get the period, we divide by 10. So that's what I did over here. So this is the time for 10 vibrations. I divided by 10 to get the actual period. And I looked ahead, and they have t squared. And I looked at their graph. Their graph is t squared. So that told me that to linearize this data, that they want me to square everything. So that's going to be t squared equals 4 pi squared, and that's going to be m over k. But I'm going to slide the k over here like this. Because now when I look at their graph, y equals mx, and again, the plus b is supposed to be 0. And if it's not 0, it means I just have some experimental error. So you'll notice that they put t squared on the y-axis. They put the masses on the x-axis. So the slope is going to be equal to 4 pi squared over k. So I'm going to flip that over. All right, letter B. On the graph below, plot t squared versus mass. So I plotted my green points, t squared and mass. So that's these t squareds, and that's mass and t squared. So I plotted my points. Draw on the graph the line that is your estimate of the best straight fit line to the data points. I'm going to give you a little tip. You are supposed to bring a ruler, a straight edge, to your AP exam for this exact reason. They want that line to be perfectly straight. So you don't get to sketch it. You got to use a ruler. And when they correct it, they try to make sure that you have the same number of points above the line as you have below the line. So use that as a little clue. Unfortunately, in this example, we have 1, 2, 3, 4, 5 points. So I really couldn't make sure that I had the same number above and below. But if you have an even number, that's how they determine if you did a good best fit line. All right, so there's my best fit line. All right, an object whose mass is not known. This is what we did in class. We pretended that we found a moon rock and we're at the moon and we can't use a gravitational balance to find the mass, so we have to use our inertial balance. So I would take my moon rock then and I would put it on the balance, attach it to something in the spaceship, and let it boing up and down 10 times. So it boinged up and down 10 times, and the average time for 10 vibrations is 16.1 seconds. From your graph, determine the mass of our moon rock. So I'm talking to myself. It took 16.1 seconds for 10 vibrations. That means the period was 1.61 seconds. But my graph is in period squared. So when I square 1.61, I get 2.59. That's right there in blue. So 2.59, I'm going to go over, and then I'm going to look at my best fit line, and I'm going to go down and read the mass right off my best fit line. The mass of the moon rock is 0.45. So that's what's cool about the inertia balance. All you need is the best fit line, and you can find the mass of anything out in space. Now, instead of taking the graph with you out in space, sometimes it's more convenient to take the linear regression equation with you out in space. I'll come back to that in a minute. So determine the slope of the best fit line by hand and by using linear regression. We need to be able to find the slope both ways. And I know you know how to find slope, but we have to start doing a really, really good job that our answers are very, very similar. So that's what we're doing here. We're checking how close can you get. So when you find the slope of the line by hand, you can never use data points. You can never use data points from the data table. You can't like do rise over run or subtract the first and the last data points. You have to pick 2 points on your best fit line. And so they like you to circle the points that you're using. So I circled this point and I circled this point because my best fit line kind of seemed to be going through the corners there a little bit. And so when I found my slope by hand, I found a 6. Then I put it in my calculator and did linear regression. When I put it in the calculator, I had to put masses on the x for my x values, and t squareds is my y. So these were my x's, and these were my y values. And I used my calculator, I did linear regression, and I get y equals 5 whatever. So my slope is 5.73. The real slope is 5.73. When I did it by hand, I got 6. So I did not do a great job there. But let's look at this y and the x. This is something that we sometimes don't talk a lot about in class. But this y should be replaced with that t squared, because that's what's on the y-axis. T squared equals 5.73. On the x-axis is mass. And I do have some error here, 0.09, so I'm going to put that on there. And so now if I went out in space and I know that t squared was 2.59, I plug 2.59 in for that t squared value, and then I can calculate m. So all I got to take with me out in space is my regression equation, and then I can find the mass of something once I know the period, and then I square that. All right, letter E, determine the force constant of the metal plate. We already figured out that the slope is equal to 4 pi squared over k. On your AP exam, If you did it by hand, you could use that value. If you use linear regression, which I did over here, I used that value. Either one would be fine. If you do linear regression on your AP exam, if you have a choice, by hand or linear regression, you can do either one. But I want to point this out to you. If you choose to use linear regression to determine the equation of the best fit line, make sure you tell the reader what you're doing. You can't just like throw an equation down that looks like you pulled it out of the wind or copied off your neighbor's paper. You have to say a sentence like this. I use linear regression on my calculator to find the equation of the best fit line. Then you can plop it down and the reader knows exactly where this is coming from. So I get a K value of 6.89 newtons per meter. That's the force constant of the springy or the boingy piece of metal that I'm using. All right, letter F. Can this device be used to measure mass aboard the Space Shuttle Columbia as it orbits the Earth? Yes, that's exactly what the inertia balance is used for. Explain briefly. I have 3 explanations that is part of my briefly. Number 1, once you calibrate your balance on Earth, you can use the regression equation to calculate the mass on the spaceship. Number 2, period is not affected by gravity. I don't need gravity. Number 3, you don't need gravity to determine the period of something, which is why it is helpful on the spaceship. So I probably could say one statement, but if I had to say one statement, I actually like the third one best. So I kept getting better and better as I did that. All right, letter G. If the spaceship is orbiting this many meters above the Earth's surface, what is the acceleration due to gravity of the spaceship? So they gave you these numbers on the AP exam. I forgot to use those numbers. I used the numbers that we were used to in class. So what is the acceleration due to gravity of this spaceship as it's orbiting up here above the Earth? So what they're really testing you here is, do you remember the equation for acceleration due to gravity? When it's not 9.8, when it's not near the surface of the Earth. So it's gm over r squared. Gm r squared is the radius of the Earth plus how high I am squared. And we find out that gravity up here at this orbiting spaceship is 8.94. It's 9.8 on Earth. And yes, it's less up in space, 8.94, but that's not very much less. But if I looked at the people in the spaceship, they're all floating around looking like they're in free fall, but there's a lot of gravity up there. Letter H. Since the answer to G is not 0, briefly explain why the objects and the people aboard the orbiting spaceship seem weightless. Why are they floating around? So I drew a picture here of the Columbia spaceship orbiting. And when it's orbiting, it has an orbital velocity. And the velocity acts tangent to the circle. Obviously, there's an acceleration pointing towards the Earth. How do I know there's an acceleration? Because there's a gravitation, Fg, the gravitational force points to the center of the Earth. And anytime you have something in a circle, there is an acceleration towards the center of the Earth. It's the centripetal acceleration. And if you look at this picture, I'm going to turn my paper sideways a little bit. I have a velocity vector perpendicular to an acceleration vector. Just going to grab a sheet of paper here. It's not going well. All right, so if we had a cliff and we fire something horizontally with a velocity and we have an acceleration vector, we know that this object is going to projectile motion to the ground. So that's what this is doing. It's projectile motioning around the Earth. And so when something projectile motions, it's in free fall motion. And so as something orbits the Earth, it technically is in free fall motion as it orbits because these two vectors are perpendicular to each other. So I wrote down, why do they seem weightless when there really is a lot of gravity? They are in projectile motion or free falling towards the Earth as the shuttle orbits. And this is, I'm just going to circle this one. This is a key concept that they try to hide someplace in our AP exam because people don't always get that you can have a lot of gravity, but you're still in free fall motion as you orbit. All right, I think that's a good explanation for this particular problem. I hope that helped.